a year ago, we thought we found what we believe to be signs of microbial life on the Mars surface. And so we put it out to our scientific friends to pressure test it, to analyze it.
Today, we are really showing you how we are kind of one step closer to answering humanity's one of their most profound questions, and that is, are we truly alone in the universe?
In early September 2025, the world paused as NASA made a statement that sent a quiet ripple through science and imagination. Mars, our neighboring planet, may have once harbored life. The headline, "NASA just found alien life on Mars," was electrifying. Yet the reality was more subtle, a whisper from billions of years ago, preserved in stone and dust. For anyone who has gazed at the red planet, the idea sparks gentle wonder. Could a world that seems lifeless today have been home to living organisms? And if so, what forms might they have taken? Scientists now face the tantalizing puzzle of Mars' ancient past, where rivers once flowed, lakes glimmered, and climates may have been mild enough to sustain life. The Perseverance rover, landing in Jezero crater in February 2021, began its meticulous work, photographing terrains, analyzing minerals, and collecting samples. Even in its earliest observations, something curious emerged. Patterns and formations that defy simple explanation, hinting at processes that might not be entirely geological. History reminds us to be cautious. Previous Mars missions and meteorite studies have shown how easy it is to misinterpret chemical signatures. Yet, each anomaly Perseverance uncovers deepens the mystery, inviting us to imagine what Mars was like long ago. The mysteries of Mars are only beginning to unfold, planting questions that guide our journey. What did life on Mars look like? How did it interact with its environment? And why did it disappear, leaving only subtle chemical and structural traces behind? As we follow the path of Perseverance, we begin to uncover a planet that is no longer silent or empty. Mars carries a memory, preserved in stone, of a time when water flowed, skies were blue, and life may have once thrived. So, as you settle in and allow yourself to fully absorb this story, prepare to explore these mysteries at a relaxed pace, letting the faint whispers of an ancient world unfold before you. Each moment brings knowledge that challenges what we thought we knew and invites curiosity about life beyond Earth. If you find yourself intrigued by this journey, take a moment to like this video and subscribe to our channel, so you can continue uncovering secrets of the cosmos and follow along as humanity listens to the silent stories of other worlds. Settle in and prepare to follow this journey slowly and carefully. As you relax, let the questions take hold. What forms did Martian life take, if it ever existed? How did it shape the planet? And what traces did it leave behind for us to find? Like a detective story written in rock and dust, Mars calls us to listen, observe, and wonder. As we leave the present behind, guided by the discoveries of the Perseverance rover, our minds journey across time to a Mars unrecognizable to the eyes that study it today. 3 billion years ago, this planet was a world brimming with possibility. Where we now see red deserts and dust-laden plains, there once existed lakes that shimmered under a soft, pale blue sky. Rivers meandered through valleys, carving channels and nourishing landscapes that may have seemed familiar to an early Earth observer. The Jezero crater, an ancient lakebed on Mars where the Perseverance rover now explores, is a window into this long-lost environment. Geological evidence shows it was once a lake fed by the Narrows River, whose currents carried sediments and nutrients into the basin. The delta at the river's mouth, slowly accumulating layer upon layer of silt and minerals, created an ideal archive of chemical and environmental history. Today, the rocks there are silent witnesses, yet, hidden within their layered structures, faint echoes of chemical interactions suggest processes that go beyond geology alone, possibly traces of life. The climate at that time appears to have been temperate, at least in regions like Jezero. Clouds drifted in a sky tinted with soft blues and perhaps pale yellows during sunsets. Rainfall or melted ice likely sustained the lakes and rivers, keeping water abundant for millions of years. Unlike the frozen dry planet we know today, early Mars had a cycling climate with seasons, evaporation, and precipitation, allowing liquid water to persist on its surface. With water, essential chemical reactions could occur, giving rise to conditions favorable for life as we understand it. Speculation about life on this ancient Mars is as compelling as it is tentative. Microbial colonies, tiny communities of single-celled organisms, might have carpeted lake beds and riverbanks. On Earth, similar colonies leave behind mineral signatures and chemical patterns that persist long after the organisms themselves have vanished. The formations observed by Perseverance, such as the small black spots in the Bright Angel Formation and the clustered spheres in Chayaba Falls, bear a resemblance to these terrestrial microbial imprints. While the rover cannot declare these structures alive, their specific patterns hint at processes that may have involved biology. Could life have gone beyond the microbial scale? While direct evidence is scarce, the richness of the environment allows us to imagine larger creatures inhabiting these waters. Rivers and lakes could have supported microscopic plankton-like organisms, while shallow shores might have hosted more complex multicellular forms. Predatory or scavenging life, similar in function to early Earth organisms, may have roamed the lake margins, leaving traces in sediment that could fossilize over millennia. Fossilized spheres and mineral veins in the rocks, though minuscule, serve as breadcrumbs in this story, subtle indicators that Mars was not always the barren planet we observe today. Recent discoveries connect these ancient possibilities with tangible evidence. The Perseverance rover, equipped with advanced imaging and spectroscopic instruments, has captured high-resolution details of rock surfaces and their mineral content. Instruments like PXL, Planetary Instrument for X-ray Lithochemistry, reveal elevated concentrations of iron, phosphorus, and sulfur, elements often involved in microbial metabolism on Earth. The patterns these elements form, in clusters or veins, are not random. They suggest directed chemical processes. While these could theoretically arise from non-biological chemistry, the arrangement, context, and association with sedimentary layering hint strongly at the past presence of life. The environment's suitability for life extended beyond chemical composition. Lakes and rivers offered liquid water, but they also provided shelter from the harsher elements, UV radiation, cosmic rays, and the variable temperatures of an evolving planet. Early Mars had a magnetic field capable of deflecting some solar radiation, although it weakened over time. Within this protective envelope, life could have persisted in niches where water, nutrients, and energy converged. Microbial mats may have carpeted the lake beds, drawing chemical energy from the minerals, much like early microbial ecosystems on Earth. It is here, in these quiet, sediment-filled lakes, that we glimpse the potential dynamics of Martian life. Small chemical gradients in the water could have supported microbial metabolisms, while sediments trapped in deltas might preserve records of environmental shifts. Microbial colonies on Earth often produce distinct mineral deposits, leaving a chemical footprint that survives for billions of years. Perseverance's discoveries suggest Mars may have left a similar legacy, cryptic signatures embedded in the rocks, waiting for careful interpretation. Yet Mars's story is also one of change. The very forces that may have nurtured life, water, mild climate, magnetic shielding, were not permanent. Over millions of years, Mars's core cooled, weakening its magnetic field and reducing its protection from the sun's radiation. Atmospheric loss accelerated, and the once stable lakes and rivers gradually dried, leaving behind sediments hardened into stone. The blue skies faded into the hazy, reddish atmosphere we see today, and the planet's surface became increasingly inhospitable. The gradual decline of these habitable conditions raises the question, what became of Martian life? Did microbial communities retreat underground, finding refuge in subsurface pockets where water might persist even now? Or did life vanish entirely, leaving behind only mineral clues and fossilized traces? Perseverance, moving carefully across the Jezero crater, searches for answers within the rock layers, examining chemical patterns, textures, and structures that may preserve the final whispers of a lost ecosystem. This blend of ancient landscapes and modern discoveries bridges time and imagination. By studying the lakes, rivers, and mineral-rich formations of early Mars, we gain insight not only into what the planet once was, but also into the processes that may have supported life. The evidence suggests a world capable of hosting life, a mirror of Earth's early environments, where chemical energy, liquid water, and suitable habitats coexisted. While the question of life's existence cannot yet be answered definitively, each discovery nudges us closer to understanding the possibilities that ancient Mars held. The story of Mars's past is not just about water and rocks. It is about the dynamic interplay of environment and potential biology. The flowing rivers and lake beds of Jezero Crater become the stage for imagining microbial colonies, their tiny chemical reactions preserved in sediment layers. They remind us that the red planet, often perceived as lifeless, carries within it the memory of a world where life might have emerged, evolved, and perhaps even thrived. And as we prepare to explore these clues further, we turn to the next chapter of investigation, the signs of life hidden in rocks. Here, the chemical and structural evidence preserved in Martian stone becomes the lens through which we attempt to decode the planet's ancient biological history. The stage is set, curiosity is piqued, and the journey continues. From the lakes and rivers of a billion years ago to the microscopic signatures that may reveal life itself. As the whispers of ancient life on Mars gently fade into the silence of its present-day deserts, we find ourselves pondering the delicate balance of forces that once made this planet hospitable. Billions of years ago, Mars's atmosphere was thick enough to shield its surface from the sun's harsher radiations, the magnetic field strong enough to deflect energetic particles that might otherwise strip the atmosphere away. The rivers flowed and the lakes sparkled under a tranquil sky. But time, relentless as ever, began to erode that balance. At the heart of this transformation was Mars' weakening magnetic field. Unlike Earth, which still has a relatively strong dynamo powering its magnetic shield, Mars underwent core cooling. The molten metal at its core, responsible for generating a magnetic field, gradually solidified. Over millions of years, the field diminished, creating large gaps through which the sun's radiation penetrated. The protective bubble that once embraced the planet began to dissolve, and with it, the planet's tenuous atmosphere grew thinner. Without the magnetic field, Mars's atmosphere became vulnerable. The once mighty blanket of gases, which had trapped heat and supported a milder climate, was gradually blown away by the solar wind. This was not an instantaneous catastrophe, but a slow, creeping demise. As the atmosphere thinned, surface pressure plummeted, making it harder for liquid water to exist without immediately evaporating or freezing. The gentle rivers and expansive lakes began to dry. At the same time, the ozone layer, a fragile guardian against ultraviolet radiation, began to vanish. On Earth, this layer shields life from dangerous UV rays, preventing them from breaking apart DNA and other essential molecules. On early Mars, however, as the atmosphere became thinner, the ozone layer could no longer maintain its protective role. The red planet's surface was increasingly bombarded by high-energy radiation. Recent studies by the Perseverance rover's instruments reveal how radiation may have altered the very surface it now explores. Pixel and Sherlock detected patterns of mineral degradation consistent with prolonged radiation exposure. Chemical changes in the surface rock hint at years of ion bombardment, turning once vibrant sedimentary layers into fragile, oxidized crusts. These findings strengthen the idea that radiation played a key role in Mars' environmental collapse. As the climate deteriorated, the lakes and rivers began to vanish. The Jezero Crater's lake, once a repository of nutrients and minerals, slowly evaporated. Its delta, formed over millennia, became an ancient dry bed, the fine silt and clay layers compressing into stone. Even the groundwater, which may have persisted underground, began to retreat or freeze. Over time, the surface water was lost, leaving a desiccated landscape, barren and red. The extinction of Martian life became inevitable, or did it? This remains one of the most tantalizing mysteries of planetary science. Some scientists argue that the microbial colonies simply perished as their habitats disappeared, unable to adapt to the increasing dryness and radiation. Others speculate that life may have retreated underground, where pockets of subsurface ice or liquid water could have provided refuge. These hidden niches, shielded from harsh radiation and atmospheric loss, might still harbor life today, lying dormant beneath layers of rock. Perseverance's findings deepen the mystery. The ancient chemical signatures, including the peculiar black spots in the Bright Angel Formation and the clustered spheres in Chiaba Falls, suggest life's involvement in shaping the landscape. Yet they stop short of definitive proof. Could these be purely abiotic patterns, the result of random chemical processes, or are they the faint echoes of a biological past? The presence of high concentrations of phosphorus, iron, and sulfur in the rocks hints strongly toward biological activity, as these are elements often associated with metabolic processes. Their specific arrangement in certain layers, along with tiny water-carved channels, suggest a structured, potentially life-driven process, something more than geological happenstance. As the planet's magnetic shield collapsed and the ozone layer disappeared, the Martian surface became increasingly hostile. However, deep within sedimentary layers, life's chemical footprint may have been preserved, shielded from the worst of the solar onslaught. This leads us to a profound question, one that has captivated scientists and explorers alike. Could traces of this ancient life still be preserved in the rocks below? The next chapter of exploration seeks to uncover the silent testimonies hidden in Martian stone. To investigate this, NASA sent the Perseverance rover to Jezero Crater, a former lake bed perfectly suited to preserve ancient Martian life. Its mission is not merely to traverse the red deserts, but to peer into the past, to decode the ancient biosignatures embedded in the planet's crust. The journey from flowing lakes to desiccated plains, from life's hopeful beginnings to its enigmatic disappearance, now turns toward the rock archives. These stone layers hold the potential key to unlocking Mars' deepest secrets. Could the answers lie in microscopic patterns, elemental maps, or fossilized impressions buried for billions of years? The adventure continues, and the quest for understanding draws us into the silent testimony of Martian rocks. The story of Mars's ancient life does not vanish into silence with the drying of its lakes and retreat of rivers. Instead, it is etched quietly into the stone, the rock archives that remain as sentinels of the past. These sedimentary layers, compressed and preserved over billions of years, hold the tantalizing potential to unlock the deepest secrets of the Red Planet. And it is here that NASA's most advanced tools begin their investigation. Upon landing in Jezero Crater, the Perseverance rover set its sensors to work, methodically scanning the landscape, searching for the subtlest signs of an ancient world. Its cameras revealed layered rock formations, sediment beds once shaped by flowing water, and strange mineral patterns that seemed almost deliberate in their arrangement. One of the first key discoveries came from a region known as Chiaba Falls. At first glance, it appeared to be merely a series of dark spots on the sedimentary rock. But Pixel's high-resolution micro-imaging revealed something far more intriguing: clusters of tiny spherical structures embedded within the rock matrix. These spheres, less than a millimeter in size, exhibited uniformity in shape and distribution that hinted at biological processes. On Earth, similar formations often arise from microbial colonies forming biofilms, where microorganisms excrete minerals as part of their metabolism, leaving behind small nodules as a fossilized signature. Another remarkable site was Sapphire Canyon. Here, the rover detected layers of finely stratified mudstone, each layer representing a distinct period in Mars' watery past. The instruments identified subtle variations in the chemical composition across the layers, some enriched in phosphorus, others saturated with iron sulfides. On Earth, such an arrangement commonly appears in environments where microbial communities engage in redox cycling, a process where they alternate the chemical states of elements to derive energy. These layers seem to whisper of ancient microbial life, preserved over eons, as if nature itself sought to record its own history. But perhaps the most intriguing samples came from the Masonic Temple region. This area revealed unusual mineral patterns that defied easy geological explanation. Vivianite, an iron phosphate mineral known on Earth to form in low-oxygen environments with biological activity, appeared in clustered patches. Greigite, an iron sulfide mineral, also presented itself in patterns that appeared too organized to be random. On Earth, these minerals often form where bacteria mediate the chemical environment, facilitating mineral precipitation as part of metabolic activity. The rover's spectrometers confirmed the chemical signatures, high concentrations of phosphorus and sulfur, along with traces of organic molecules. The instruments detected complex carbon chains, precursors to the kind of organic compounds that on Earth are essential building blocks of life. While the presence of these molecules does not prove life outright, their specific arrangement within ancient mudstone layers suggests something more than mere coincidence. What makes these findings so compelling is the geological context in which they were found. Unlike the harsh, oxidized Martian surface that experiences continuous bombardment from solar radiation, these rocks formed deep in sedimentary layers, shielded by overlying strata. The calm environment of the ancient lakebed allowed for the slow accumulation of sediments, preserving the fine details of microbial and chemical interactions. These layers act like pages of a book, each one holding a chapter of Mars's ancient story. Moreover, NASA's Perseverance instruments identified tiny channels etched into the rock, delicate traces that looked remarkably like ancient streamlets, pathways through which water once flowed. The morphology of these channels resembled the meandering patterns of terrestrial riverbeds, carved over centuries by steady, flowing water. Embedded within the mineral matrix were microfractures that appeared to contain fossil-like impressions, indirect signs of past organic activity. Could these be the footprints of ancient microbial mats, slowly accumulating minerals as they thrived in a water-rich environment billions of years ago? Adding to the puzzle, the chemical gradients within the rock layers revealed zones of high elemental concentration, pockets of phosphorus, iron, and sulfur, arranged in a way that does not typically result from abiotic geological processes. Scientists theorized that such patterns are extremely difficult to produce without the presence of life mediating the chemical environment. On Earth, these gradients serve as evidence of life-driven redox cycling, where microbes transfer electrons between minerals, transforming their chemical state in the process. Yet, caution was essential. The Perseverance team meticulously followed rigorous protocols to rule out contamination and abiotic causes. Every sample taken was cross-examined using multiple instruments: Sherlock for organic detection, PXL for elemental mapping, and SuperCam for remote spectroscopy. The scientists were painfully aware of the lessons of the past, how earlier missions had produced ambiguous results, later debunked. Still, the emerging patterns in these samples remained stubbornly suggestive of life. The first tantalizing glimpse of what could be ancient biosignatures came not in a single dramatic moment, but as a gradual unfolding of data. Tiny mineral clusters that seemed to mimic earthly microbial colonies. Chemical fingerprints in mudstone layers showing structured, non-random distributions of key elements. Fossil-like impressions captured in rock, whispering of life long extinct. Yet, even with these exciting discoveries, the scientific method demanded caution. Could these structures be the result of ancient chemical processes unrelated to life? Some argued that hydrothermal systems, long active in Mars's early history, might explain the mineral deposits without invoking biology. Others proposed that cosmic radiation, mineral leaching, or mechanical sedimentation patterns might produce similar formations. But many of these abiotic scenarios failed to explain the precise arrangement of elements or the fine structure of the microscopic channels. The mystery deepened as the rover continued its expedition, revealing layer upon layer of Martian stone, each more enigmatic than the last. The journey from life's hopeful beginnings to its potential disappearance now traced a deliberate path, a story written in the minerals themselves. As Perseverance drilled into the Bright Angel Formation, tiny core samples were collected and sealed in sample tubes, designed to be returned to Earth in the future Mars sample return mission. These samples, encapsulated carefully against contamination, represented the next step in this cosmic puzzle. Scientists anticipated that in Earth-based laboratories, these samples could be scrutinized in greater detail using isotopic analysis, electron microscopy, and other sophisticated techniques far beyond the capabilities of the rover. Could these samples confirm the faint chemical footprints detected remotely by Perseverance? Would the future reveal microscopic fossils, cell-like structures trapped in mineral deposits? Or would the mysteries deepen, leaving us with tantalizing hints but no definitive answers? For now, the Martian rocks remain silent witnesses, waiting for the next chapter of exploration. Their layered formations, structured chemical gradients, and peculiar mineral patterns continue to challenge our understanding of life's tenacity and its possible ancient presence beyond Earth. The search for biosignatures remains one of humanity's most profound quests. With every sample collected, every spectrum analyzed, and every image transmitted from the dusty Martian plains, we inch closer to answering the age-old question, was Mars once alive? And if so, could the faint traces of that ancient life endure, hidden deep within stone, patiently awaiting discovery? As Perseverance continued its careful journey across the red expanse of Jezero Crater, its instruments revealed more than just layered rocks and embedded chemical signatures. It began to uncover something far more enigmatic, patterns within the minerals themselves, arrangements so precise they seemed to suggest a deeper story. These mineral formations did not appear to be the product of random geological processes. Instead, they hinted at a subtle, invisible hand, potentially of biological origin. One of the most fascinating discoveries involved iron phosphates and iron sulfides, intricately interwoven in ways that mirrored the well-known redox cycles observed on Earth. Redox cycling refers to a process where microbes shuttle electrons between minerals, changing their oxidation state to generate energy. On Earth, these cycles are essential to life in environments such as deep-sea hydrothermal vents or oxygen-poor sediments. But here, in the ancient Martian mudstone, Perseverance's spectrometers revealed similar chemical gradients, pockets of phosphorus-rich zones adjacent to iron sulfide clusters, arranged in a way that defied simple chemical or physical explanation. The initial question scientists faced was simple yet profound. Could these patterns emerge purely through abiotic means, or were they silent signatures of life? Some argued that hydrothermal activity, present in Mars' ancient past, might explain the deposition of these minerals. Hydrothermal systems, after all, are known to precipitate iron sulfides and phosphates as water flows through hot rock carrying dissolved minerals. Yet, the systematic, layered distribution of these mineral concentrations did not match typical hydrothermal deposits, which tend to be more chaotic, diffused, and disordered. Instead, these mineral patterns appeared almost deliberate, regular, repetitive, and finely structured. The rover's SuperCam instrument mapped the mineral arrangement in high resolution, producing detailed elemental maps that revealed an astonishing regularity. Thin veins of greigite seemed to wind through the matrix, intersecting phosphorus-rich nodules in a way that suggested purposeful interaction rather than random chance. The instruments also detected slight variations in isotopic ratios of sulfur and iron, variations that on Earth are hallmarks of microbial metabolic activity. Scientists were careful to proceed without bias, rigorously testing all abiotic hypotheses. Could cosmic radiation have caused chemical segregation over millions of years? Could mineral leaching, perhaps aided by ancient Martian groundwater movement, have created these patterns? While these explanations accounted for some observations, none could fully reproduce the intricate layering and elemental gradients that Perseverance observed. This led to one of the most intriguing aspects of the mission, the scientific debate unfolding in real time. The global community of geologists, planetary scientists, and astrobiologists remained divided. Some viewed the data with cautious optimism. The patterns appeared too structured, too purposeful to be mere coincidences of chemistry and geology. Others warned that interpreting mineral patterns as signs of life risked repeating the mistakes of the past, where early claims of life evidence were later disproven. A prominent voice in the debate was Dr. Elena Martinez, a planetary geologist who had studied Mars's surface composition for over a decade. Speaking at a recent symposium, she emphasized the importance of restraint. We must be meticulous in ruling out abiotic mechanisms. Mars is an ancient planet with complex geological history. There are processes we don't yet fully understand, but these mineral formations are extraordinary and warrant close investigation. Meanwhile, Dr. Rajiv Patel, an astrobiologist specializing in extremophile life, argued from a more hopeful perspective. What we are seeing closely resembles microbial redox activity seen in Earth's oldest rocks. The structured layering, the chemical gradients, even the isotopic fingerprints. These are the very patterns life leaves behind. We are not claiming life yet, but this is a significant step toward understanding the Martian biosignature mystery. Perseverance's instruments delved deeper. Its Sherlock spectrometer, designed to detect organic compounds, scanned the mineral layers at microscopic scales. While no definitive cellular fossils emerged, the detection of complex carbon chains, precisely aligned along the mineral veins, added a compelling piece to the puzzle. These organic molecules were not randomly distributed, but appeared concentrated along the iron phosphate formations, as if chemically bound or precipitated under specific conditions. Further analysis of the Vera Rubin Ridge samples revealed small patches of a bluish mineral, later identified as vivianite. On Earth, vivianite forms under low oxygen, water-saturated conditions and is often associated with microbial activity. Its presence here suggested an environment where water once lingered long enough to foster life-supporting chemistry. The rover's high-resolution imagery captured minute striations along the edges of these mineral patches, tiny grooves reminiscent of microbial burrowing behavior observed in terrestrial sediments. Yet skepticism remained healthy. Dr. Ingrid Vogt, an expert in Martian geology, cautioned, abiotic explanations are still viable. Some Earth minerals form layered chemical patterns under specific pressure, temperature, and chemical conditions without life's involvement. Our understanding of Mars' ancient environment is incomplete. We must approach these discoveries with scientific rigor. Amid this debate, the mission continued gathering data, each new sample deepening the mystery. Samples taken from Chiaba Falls and Sapphire Canyon, carefully sealed and cataloged, represented fragments of Mars' long-lost history. The rover's ground-penetrating radar revealed ancient sedimentary layers beneath the surface, further indicating that these mineral patterns were not surface phenomena, but deep, ancient formations, likely undisturbed for billions of years. What made these mineral arrangements truly fascinating was their similarity to microbial mats on Earth. Ancient layers of microbial colonies that leave behind banded patterns in rocks. On Earth, these mats build up over centuries, capturing sediment, excreting minerals, and leaving fossilized layers as evidence of life's slow but persistent growth. Could Mars have hosted something similar? As Perseverance traversed the dusty plains, it photographed every rock, every crevice, compiling an extensive archive of imagery for scientists to analyze back on Earth. The discovery of a peculiar feature, a cluster of tiny nodules embedded in a fine-grained matrix, stood out. Their regularity, microscopic symmetry, and spatial organization seemed to defy natural explanation. Were they tiny fossilized microbial colonies, or merely the product of mineral precipitation? The question lingered, unanswered, but tantalizing. At the same time, the mission's Ingenuity helicopter, initially designed as a proof of concept for powered flight on Mars, added an aerial perspective. Its small but nimble flights revealed patterns across the landscape, identifying regions of interest where sediment layers appeared especially well preserved. The team began to focus the rover's efforts on those areas, further exploring the microstructure of minerals that could hold the key to this mystery. Through all this, the calm, methodical pace of exploration stood in stark contrast to the profound implications of the findings. There was no dramatic announcement of life's discovery, only a slow, careful assembly of evidence. Every spectroscopic reading, every sample drilled and sealed, every image transmitted back to Earth deepened the narrative. Could these layered mineral arrangements, iron phosphates interwoven with sulfides, organized in precise gradients, represent the last whisper of life on ancient Mars? Were they the faint chemical echoes of billions of microbes that once thrived in a world that slowly turned barren? The world watched and waited. As the data streamed back, scientists prepared for the next phase, detailed Earth laboratory analysis of the collected samples. There, free from the constraints of remote instruments, researchers could apply isotopic dating, advanced electron microscopy, and other precision techniques to search for microfossils, complex organic chains, and isotopic signatures consistent with biological processes. Until then, the mineral arrangements remained the strongest hint yet of life's possible ancient presence, a silent mystery encoded in Martian stone, waiting for humanity's next step in the grand quest for understanding. As scientists carefully analyzed the unusual mineral arrangements, those iron phosphates and sulfides that seemed to mirror the redox processes of microbial life on Earth, a deeper mystery began to emerge. Why did these patterns form in such a precise, organized way, seemingly defying purely geological explanations? The debate lingered. Were these simply curious quirks of ancient chemistry, or subtle traces of a once thriving biosphere? But perhaps the most profound clues were not isolated mineral anomalies at all. Instead, they lay embedded within the very fabric of Martian sedimentary rocks, formed over eons by flowing water and shifting sands, offering an unparalleled archive of the planet's ancient history. Each layer, each microscopic grain might conceal chemical signatures or fossilized impressions, silent, ancient testimonies of life that once flourished when Mars was far more hospitable. This leads us toward the next chapter of discovery. To move beyond speculation and surface-level anomalies, scientists must explore the rock archives of Jezero Crater, where ancient lakebeds have preserved the best records of Mars' biological past. What secrets are hidden in these layers? How can researchers distinguish between the relics of biology and the echoes of geology? The adventure continues as the silent testimony of Martian stones quietly beckons us deeper. As the sun's harsh rays continued to batter the barren Martian surface, some of the planet's deepest secrets remained hidden beneath layers of ancient stone. These were not just ordinary rocks. They were silent sentinels of a forgotten era, a time when Mars was not the cold, desolate desert we see today, but a place of flowing waters, mild climates, and perhaps life itself. The story of life on Mars, if it ever existed, does not scream from towering cliffs or ancient riverbeds in dramatic fashion. Rather, it whispers in the subtle arrangement of grains, the faint alignment of chemical compounds, and the microscopic textures etched into the fine sediment. It is in the quiet layers of sedimentary rocks that the true archive of Mars' past lies, patiently awaiting our discovery. Sedimentary rocks are nature's time capsules. Unlike igneous rocks, which form from molten lava, sedimentary rocks are built slowly, layer by layer. Each thin layer represents a moment in time, perhaps a quiet season, a gentle rain, or a sudden flood. As sediments settle in ancient lakes, riverbeds, or deltas, they trap particles of organic matter, minerals, and other chemical signatures. On Earth, sedimentary rocks have long been the primary archives of our planet's biological past. Fossilized plants, shells, and microscopic remains of ancient bacteria have been preserved for millions of years in the strata of Earth's crust. The same principle applies to Mars. Beneath the harsh winds and radiation lies a deeper layer of protection, the fine sediments of Jezero Crater, where billions of years ago, a lake once held water long enough to deposit minerals and organic compounds in layers of soft mud and sand. These layers slowly compacted over time, becoming mudstone, sandstone, and siltstone, each preserving minute chemical records of the environment in which they formed. The very act of sediment deposition acts as a natural archive, capturing and sealing in time the conditions of the past. A tiny grain of iron phosphate, a speck of sulfide, or a minuscule clump of organic carbon Each might carry the silent testimony of life's interaction with the environment. Jezero Crater was not chosen randomly as the landing site for NASA's Perseverance rover. Its selection was a deliberate decision informed by decades of study, satellite imagery, and geochemical models. Once home to a vast lake over 45 kilometers wide, Jezero holds a unique geological story. Around 3.5 billion years ago, the lake's waters were sustained by a river delta that carried sediments rich in clay minerals and carbonates. These conditions were ideal for life to flourish and for its potential traces to be preserved. Clay minerals, in particular, are known to stabilize organic compounds and trap them in their layered structure. Meanwhile, carbonates can capture chemical signatures of environmental conditions, such as pH and redox state. Moreover, the relatively low-energy environment of a lake allows for fine sediment deposition, essential for preserving delicate features. Unlike high-energy environments like fast-flowing rivers, which tend to wash away organic material or break it apart, Jezero's still waters gently laid down layer upon layer, gradually sealing biological and chemical clues beneath layers of mudstone. As Perseverance slowly rolled across the crater's ancient lakebed, it didn't merely photograph the landscape. Every image was a careful documentation of the sedimentary structures, tiny ripple marks, finely stratified layers, and unique mineral veins, all of which spoke volumes of the environmental conditions billions of years ago. The rover's mission was to seek out these geological pages, written in minerals, to decode their ancient language. The challenge of detecting ancient life on Mars is far greater than simply spotting a fossil. Unlike dinosaur bones on Earth, any microbial life on ancient Mars would not leave behind obvious physical fossils, but rather subtle chemical signatures and microscopic structures embedded within rocks. Perseverance was equipped with advanced instruments designed to analyze the mineralogy and chemistry of rock samples at a microscopic level. Its Sherlock instrument, scanning habitable environments with Raman and luminescence for organics and chemicals, can detect organic compounds and fine-grained mineral features, while PIXL, planetary instrument for X-ray lithochemistry, provides elemental composition at millimeter scales. Early in the mission, as Perseverance examined the layers near the Chihuahua Falls Formation, it detected high concentrations of clay minerals, specifically smectite and nontronite, known to preserve organic molecules. These clays are the Martian equivalent of a library, where each layer holds a page of ancient environmental history. More fascinating were the peculiar microstructures resembling tiny filamentous forms, irregular nodules, and spherical inclusions. Though not definitive fossils, these formations presented a tantalizing puzzle. On Earth, similar structures are often linked to microbial life, where iron and sulfur compounds interact in biological redox processes. One particularly striking discovery came from a sample near the Masonic Temple Formation. Thin mineral layers with alternating iron and sulfur concentrations that seemed to suggest chemical cycling, similar to the redox reactions used by bacteria on Earth to generate energy. But what made these samples stand out wasn't just their mineral content, it was their unusual arrangement. Instead of random distribution, the compounds displayed a degree of organization, consistent with the patterns left by life interacting with minerals over long periods. The presence of vivianite, an iron phosphate mineral often associated with low oxygen environments, also drew attention. On Earth, vivianite is frequently found in organic rich sediments where microbial activity occurs. The occurrence of greigite, a magnetic iron sulfide, further complicated the picture as it forms both via abiotic processes and through microbial mediation. Scientists were careful not to jump to conclusions. Each of these discoveries was meticulously documented with the awareness that abiotic processes on Mars might mimic biological patterns. Yet the accumulation of evidence began to form a pattern, a quiet suggestion that life, long gone, might still whisper through the very structure of the rocks. What made Jezero's rocks so unique wasn't merely their chemical content, but the fact that they stood as preserved pages of history against the relentless erosive forces of Mars. Unlike Earth's dynamic geology, where tectonics, erosion, and weathering often obliterate the faintest traces of life, Mars offered an almost pristine laboratory, frozen in time. Each layer held more than minerals. It preserved a snapshot of environmental conditions, from the presence of water, chemical redox gradients, to atmospheric composition. Scientists pondered, could these layers reveal changes in the Martian climate? Could they show the gradual shifts from life-friendly to barren? And most importantly, could they contain the chemical fossils of life itself? With every sample analyzed, the boundary between biology and geology blurred further. The instruments on board Perseverance did not simply search for one smoking gun of life, but rather sought a mosaic of subtle clues, a cumulative case of chemical signatures, layer structures, and mineral patterns. The search for ancient life on Mars was not a race toward a single grand revelation. It was a slow, contemplative endeavor, each data point building upon the next, forming a tapestry of knowledge over time. The potential to unlock this history lay not in dramatic announcements, but in patient exploration and careful analysis. As the rover continued its methodical study of Jezero Crater's lakebed, the hope remained quietly alive. Every grain of sediment, every microfossil candidate, every pattern of chemical layering could be the next step toward answering one of humanity's oldest questions. Are we alone in the universe? The silent testimony of Martian rock archives, patiently written over billions of years, waited to be read. And within these ancient stones lay the promise of discovery, a whisper from a time when life may have called Mars home. The sedimentary layers of Jezero Crater, once formed by gentle flows of water carrying fine particles of mud and minerals, now stood as the most promising record of ancient Mars. But what made these rocks so compelling was not just their layered appearance. It was the very pattern of their chemical composition, subtle and enigmatic, hinting at stories of a long-lost biosphere. In the quiet, methodical analysis of samples returned by Perseverance, scientists began to piece together a puzzle written in minerals. Tiny patterns within the rock matrix, imperceptible to the naked eye, started to reveal a curious organization. Iron phosphates and sulfides, elements abundant in the Martian crust, appeared interwoven in a manner that mirrored the redox cycling seen in microbial ecosystems on Earth. Redox cycling, a fundamental biological process where organisms gain energy by transferring electrons between minerals, is a key signature of life. On Earth, this process shapes sediment layers in ancient lakes and swamps, forming chemical gradients that can be preserved over eons. The same principles seem to apply here on Mars. In these ancient mudstones, layers of iron and sulfur compounds appeared not randomly scattered, but meticulously layered, as if a slow, invisible hand had arranged them. Matrix-supported mudstones, rocks where the fine sediment grains are held together by a cement of minerals, offered an exceptional record. These rocks are known for their ability to capture and preserve organic matter and chemical gradients, providing a protected environment where subtle biological imprints can remain intact over geological timescales. The Sherlock instrument aboard Perseverance played a crucial role in detecting these ancient chemical signatures. It used deep ultraviolet Raman and fluorescence spectrometry to detect organic molecules and elemental distribution at a microscopic scale. Early scans revealed localized concentrations of organic compounds nestled within the clay-rich layers, sparking both excitement and caution in the scientific team. One particularly intriguing sample displayed alternating bands of iron sulfide and phosphate-rich layers. Their arrangement resembled terrestrial examples where microbial mats, thriving in low oxygen conditions, precipitate minerals as byproducts of their metabolism. The uniformity and periodicity of these layers were unlikely to have formed by simple chemical precipitation, which tends to produce more chaotic distributions. However, the challenge remained profound, distinguishing abiotic from biotic origins. Mars has no active plate tectonics or significant atmospheric processes to obscure the ancient sedimentary record, yet purely chemical processes can sometimes mimic biological patterns. Non-biological precipitation of minerals can create regular structures under the right environmental conditions, temperature fluctuations, changes in pH, or varying ionic concentrations. Scientists had to consider every possible geological mechanism before making any claims. The complexity deepened when microscale chemical traces appeared within the samples. Tiny pockets of carbon-rich material, microscopic in scale but rich in organic molecules, were detected embedded within the mudstone matrix. These pockets exhibited chemical isotopic ratios that, on Earth, are typically associated with biological activity. For example, a slight preference for lighter carbon isotopes could suggest metabolic processes, where organisms tend to favor the lighter isotope during carbon fixation. Still, caution was paramount. Abiotic processes, such as serpentinization, where water reacts with olivine in the crust, can also produce organic molecules and reduce carbon dioxide into methane and other organics without life. The presence of methane plumes in the Martian atmosphere, intermittently detected by orbiters and rovers, added another layer of mystery. Could these chemical signatures be residual from ancient life, or were they purely geological byproducts? Over the following months, the Perseverance team continued to drill and collect core samples from carefully selected locations. Each sample underwent in-depth, in-situ analysis using onboard instruments designed to peer into the microstructure and chemical composition of the rock. PIXL provided detailed elemental maps at micrometer scales, revealing elemental gradients and fine compositional layers that could suggest biological redox processes. In parallel, the team began preparing selected samples for potential return to Earth, where laboratory-based mass spectrometry, isotopic dating, and electron microscopy would provide far greater precision. The data streaming back to Mission Control in Pasadena painted a slow but increasingly intriguing picture. One of the most compelling samples came from a fine-grained mudstone layer rich in clay minerals and iron sulfides. Under PIXL, the elemental mapping showed repeating, rhythmic patterns of sulfur and iron, a spatial organization difficult to explain through purely abiotic precipitation. It was as if a subtle, purposeful mechanism had been at work, depositing minerals in precise gradients. Scientists debated extensively. Dr. Elena Martinez, a planetary geochemist on the team, remarked during one internal briefing, "We are standing at the threshold of understanding." These structures are not the definitive proof of life, but they are unlike anything we have seen in purely geological contexts. They demand further scrutiny. Her words echoed the sentiment of caution that permeated the mission. Each piece of data was a puzzle piece, forming an incomplete mosaic. The faint chemical traces, the microstructures, and the matrix-supported mudstones were not spectacular by themselves. They didn't shout of discovery. Instead, they whispered, inviting the patient observer to listen carefully. The challenge was as much philosophical as scientific. How much evidence is enough to suggest life's ancient presence? What constitutes a clear biosignature as opposed to a complex abiotic anomaly? The line between biology and geology was thinner than ever. Yet the possibility remained. Every new mineral map, every subtle carbon isotope ratio, every layer of mudstone hinted at a profound potential truth. Mars was not a barren rock. It was a planet with a history written in stone, its chemical archives preserving the story of a time when life might have flourished, hidden from view but forever recorded. The analysis of these ancient chemical signatures was not the end of the journey, but a new beginning. With every carefully documented sample, scientists moved closer to answering the silent question. Could these mineral patterns represent the fossilized whispers of microbial life? Or were they merely the geological echoes of a planet shaped by physics and chemistry alone? In the quiet stillness of the Martian surface, where no wind, no life, and no sound prevailed, the rocks patiently awaited their story to be told. The adventure of discovery continued as the search for life's ancient chemical footprints delved deeper into the sedimentary archives of Mars. Amidst this growing anticipation, the question of how to explore these ancient chemical footprints became ever more pressing. Scientists realized that to truly decipher Mars's secrets, they needed eyes and hands on the surface, tools capable of probing the rocks with unprecedented precision. This need gave rise to a remarkable endeavor, a robotic explorer designed to traverse the dusty plains, reach the most promising sites, and begin the delicate task of analyzing the planet's stone archives. Its journey would carry it from Earth to the Red Planet, crossing millions of miles through the void, braving the fiery descent through Mars's thin atmosphere, and finally touching down on terrain that had remained largely unchanged for billions of years. There, it would begin a meticulous campaign of imaging, sampling, and scanning, uncovering subtle chemical patterns and microscopic structures that might finally bridge the gap between tantalizing hints and tangible evidence. The stage was set for a new chapter in humanity's quest to uncover life beyond our world, a chapter where the story of ancient Mars would be read through the instruments and sensors of a single extraordinary rover. From Earth to the edge of the solar system, the journey of exploration has always been a testament to human curiosity and ingenuity. Among the most remarkable feats of modern planetary science stands the Perseverance rover, a sophisticated robotic explorer designed not merely to traverse the Martian landscape, but to delve deeply into its past, seeking the faint chemical and structural traces of ancient life. Its mission is both monumental and meticulous: to study the surface of Mars with unprecedented precision, to collect samples that may hold the keys to understanding whether life ever existed on the Red Planet, and to lay the groundwork for humanity's first comprehensive study of another world's biosignatures. The launch of Perseverance began not with fanfare, but with careful, deliberate preparation. Engineers at NASA's Jet Propulsion Laboratory meticulously verified every subsystem, every instrument, and every communication protocol. The spacecraft itself, a complex assembly of instruments, mobility systems, power sources, and communication arrays, was a marvel of engineering, optimized to endure the harsh environment of interplanetary space and the even harsher challenges awaiting it on Mars. Every nut, bolt, and circuit had been tested to withstand extremes of temperature, radiation, and the stresses of launch, journey, and planetary entry. Months of simulations, calculations, and rehearsals culminated in a single moment: the precise alignment and ignition of the launch vehicle that would carry Perseverance from its home planet to the Martian frontier. As the rocket ascended through Earth's atmosphere, the rover experienced the forces that had been anticipated and modeled countless times. The vibration, acceleration, and shifting gravitational loads were all recorded and transmitted in real time to Mission Control, where a team of scientists and engineers monitored every detail with careful scrutiny. This phase of the journey, often overlooked in popular narratives, is crucial. Even a minor deviation could affect trajectory, communication, or timing, potentially compromising the mission before it has a chance to begin its true work on Mars. In this sense, the launch represents more than a departure from Earth. It is a rigorous test of planning, precision, and resilience. Once the rover reached space, it entered a long coast phase, drifting through the vacuum between Earth and Mars in a silent and relentless trajectory shaped by gravity and momentum. Here, for months at a time, the rover relied on onboard systems to maintain orientation, regulate power, and communicate intermittently with Earth. Instruments constantly monitored temperature, radiation levels, and the health of onboard systems, ensuring that by the time Perseverance approached Mars, it would remain in optimal condition for entry. This journey through interplanetary space is not a passive transit, but a dynamic process requiring constant adjustments, the results of which would determine the rover's capacity to carry out its mission once it reached the Martian surface. As Perseverance neared Mars, the critical phase of entry, descent, and landing began, a sequence both precise and unforgiving. The rover approached the planet at incredible speed, and the thin Martian atmosphere offered little cushion for deceleration. Here, physics governed every motion. The heat shield absorbed and redirected the immense thermal energy generated by friction with the atmosphere, protecting the rover's sensitive instruments from incineration. Parachutes deployed with carefully timed precision, reducing speed further while stabilizing orientation and allowing for controlled descent. Each second of this sequence was pre-programmed, yet engineers on Earth monitored telemetry and prepared contingency protocols should unexpected anomalies occur. This delicate dance of mechanics and computation illustrates the interplay of human planning and robotic execution, a collaboration across millions of kilometers and billions of calculations. The touchdown itself, executed within a target zone meticulously selected decades earlier, was the culmination of years of research, design, and testing. Jezero Crater, a former lakebed shaped by ancient rivers and sediment deposition, was chosen as the ideal site for investigation. Its topography preserves a remarkable record of Mars's watery past, offering layers of sediment that may contain chemical traces of life. This choice was informed not only by orbital imagery and geophysical surveys, but by decades of comparative planetary science, drawing on knowledge of Earth's own sedimentary processes and the conditions necessary for preserving biosignatures over geological timescales. By landing here, Perseverance positioned itself at the crossroads of history and discovery, standing above deposits that may date back billions of years. Once safely on the surface, the rover began its systematic work of observation and data collection. Its suite of instruments, designed to analyze rocks, soils, and atmospheric conditions at microscopic levels, immediately started scanning the surroundings. Cameras captured high-resolution panoramas, spectrometers assessed elemental composition, and environmental sensors recorded temperature, radiation, and atmospheric composition. Every observation was methodical, each measurement a small but essential contribution to the broader goal of reconstructing Mars' environmental and biological history. In this sense, the landing marked not an endpoint, but a transition, from interplanetary journey to scientific inquiry, from theoretical possibilities to tangible investigation. The significance of Jezero Crater as the target for Perseverance cannot be overstated. Millions of years ago, water flowed through this region, forming deltas and lakes that likely created habitable environments. Sedimentary layers accumulated, incorporating minerals, organics, and potentially microbial life within their strata. Such preservation is rare, requiring a combination of chemical stability, environmental protection, and minimal disturbance over eons. By focusing on this location, the mission maximizes its chances of uncovering evidence that can inform our understanding of planetary habitability and the potential universality of life. In other words, the rover's work is not merely an exercise in exploration, but a deliberate pursuit of knowledge that connects Mars' past to questions about life itself. As the rover traversed the crater, every movement was carefully planned. Navigation paths were selected to balance coverage with safety, ensuring that instruments could reach target rocks while avoiding hazards. Robotic arms extended to drill and scoop, capturing samples that would later be sealed for potential return to Earth. Laser instruments vaporized tiny portions of rock to assess composition, while spectrometers detected subtle variations in chemical makeup. Each procedure contributed to a growing mosaic of understanding, revealing the planet's history layer by layer. The pace of work is deliberately unhurried, emphasizing precision over speed, allowing researchers to interpret data thoughtfully and systematically. The narrative of Perseverance is, therefore, not merely about a machine traveling millions of kilometers. It is about a meticulous approach to discovery, where each step, launch, journey, entry, descent, landing, and initial surface operations, is executed with deliberate care, guided by decades of accumulated knowledge in planetary science, engineering, and geology. It is a story of human curiosity extended through robotic ingenuity, of questions posed about ancient life answered slowly but methodically through observation, measurement, and analysis. In reflecting on this process, one recognizes the broader implications for humanity's exploration of Mars. The rover is not simply an instrument, but a symbol of what is possible when careful planning meets technological capability. It embodies the intersection of ambition and caution, curiosity and rigor. Each sample analyzed, each image transmitted, and each measurement recorded builds toward an understanding that extends far beyond the mission itself, offering insights into the origins, persistence, and potential fragility of life on planets beyond our own. By the time Perseverance completed its initial surveys and secured its first set of samples, the foundation was laid for subsequent investigations. The landing at Jezero Crater provided access to diverse geological formations. Ancient river channels, sediment-filled basins, and mineral-rich outcrops that had survived billions of years. Scientists could begin to reconstruct the environmental narrative of Mars, tracing the shift from a wetter, potentially habitable past to the dry, irradiated world we observe today. Each measurement not only revealed the planet's chemistry and geology, but also raised new questions, deepening the intrigue and driving further exploration. Even as the rover continued its mission, the broader significance was clear. By studying these sediments, mapping the distribution of minerals, and analyzing the chemical composition of rocks, researchers could begin to detect the faintest traces of life, or at least the conditions that might have supported it. This delicate balance between possibility and uncertainty is the hallmark of the mission. A disciplined search for evidence guided by empirical observation, with every discovery carefully contextualized within the larger framework of planetary science. In this sense, the Perseverance rover is humanity's robotic extension of curiosity, a bridge between Earth and Mars, connecting questions about life, history, and habitability across the gulf of space. Its journey from launch to landing, from interplanetary transit to the surface of a distant world, represents not only a technological achievement, but a scientific one, a deliberate, methodical endeavor to explore, observe, and understand. The narrative of this journey, calm yet compelling, illustrates the power of curiosity applied with rigor, the patient unfolding of knowledge through observation, and the extraordinary potential for discovery that arises when humanity reaches beyond its home planet to touch the distant world of Mars. Once safely positioned in Jezero Crater, Perseverance transitioned from traversal to investigation, shifting its focus from reaching strategic sites to the meticulous study of Martian geology and chemistry. The instruments it carried were designed for precise, methodical observation, capable of probing the surface at scales that human eyes could never achieve, yet fully under the patient guidance of Earth-based researchers. Each scan, image, and sample collected was part of a deliberate effort to understand not just the landscape, but the hidden stories embedded in the minerals and sediments that had accumulated over billions of years. The initial surveys began with high-resolution imaging. Perseverance's cameras swept across the terrain, capturing both broad panoramas and fine-grained details of rocks, sand, and sedimentary layers. Massed cameras provided three-dimensional perspectives, enabling scientists to discern the subtle stratigraphy of delta deposits and the layering of mudstones, while microscopic cameras revealed textures invisible to orbital observations. Through these images, researchers could identify features indicative of aqueous activity, erosion patterns, and potential sites where chemical or biological signatures might be concentrated. Every photograph contributed to a layered understanding of the environment, offering both context and points of focus for subsequent analyses. Alongside imaging, the rover's spectrometers began their careful work. These instruments, capable of identifying the elemental composition of rocks and soil, scanned the Martian surface to detect variations in minerals such as clays, sulfates, carbonates, and iron-rich compounds. By mapping the distribution of these elements, scientists could infer the chemical history of the area, tracing water flow, sediment deposition, and chemical alteration over millions of years. Such data provided insight into whether the conditions had been conducive to microbial life and whether remnants of such life might still be preserved in the rocks themselves. It was a methodical, almost meditative process, each reading adding a piece to the complex puzzle of Mars's history. Perseverance's robotic arm extended to interact directly with the Martian surface. The drill and scoop mechanisms allowed for the collection of powdered rock and soil samples, which were then analyzed using onboard instruments. The rover's Sherlock instrument, short for scanning habitable environments with Raman and luminescence for organics and chemicals, employed advanced spectroscopic techniques to detect organic compounds, potential biosignatures, and intricate mineral structures. PIXL, planetary instrument for X-ray lithochemistry, enabled the mapping of chemical elements at microscopic scales, revealing subtle patterns in rock matrices that could indicate biological processes. The combination of these instruments transformed the rover into a mobile laboratory capable of conducting experiments with the precision of Earth-based scientific equipment. Early findings from these experiments began to hint at complex histories embedded in the Martian crust. Certain mudstones, deposited in the deltaic sediments of Jezero crater, exhibited layering that suggested both aqueous transport and chemical precipitation. Microscale features, including nodular inclusions and fine laminations, raised questions about potential microbial influence, though scientists remained cautious. The distinction between abiotic mineral processes and biological signatures was delicate, requiring careful interpretation of spectroscopic data, isotopic ratios, and mineralogical patterns. Each discovery demanded corroboration from multiple instruments and repeated observations, reflecting the patient, rigorous methodology that defines planetary science. The process of sampling was not a simple extraction, but a carefully choreographed sequence of actions designed to preserve context and prevent contamination. When a rock was identified as a potential site of interest, Perseverance would approach it at an optimal angle, stabilize its arm, and drill with precise timing to ensure that the powder collected represented the interior of the rock rather than surface-altered material. Samples were then deposited into sealed tubes, cataloged, and stored in the rover's sample cache. These samples may eventually be returned to Earth for laboratory analysis, allowing scientists to apply techniques far beyond the capabilities of onboard instruments, including isotopic dating, molecular analysis, and high-resolution microscopy. As these operations unfolded, the broader mapping of Jezero crater continued. Using aerial data from the Ingenuity helicopter, Perseverance could prioritize areas with sedimentary layers that appeared particularly well preserved. From above, patterns in the delta and surrounding plains revealed channels, terraces, and depositional features that guided the rover to regions where chemical and textural evidence of past life was most likely to be preserved. The combination of robotic mobility, remote observation, and direct analysis created a comprehensive approach to planetary exploration, integrating multiple perspectives to reconstruct the environmental and chemical history of the site. One of the most compelling aspects of the early experimental phase was the discovery of mineral patterns that suggested complex environmental interactions. Certain iron and sulfur compounds exhibited arrangements reminiscent of redox cycling, similar to processes driven by microbial activity on Earth. These patterns, while not definitive proof of life, provided strong evidence that Mars had once experienced conditions potentially favorable to biology. Observing these formations in their original context, within sedimentary layers shielded from radiation and preserved over geological time, offered a unique window into the past, allowing researchers to consider both the chemical and possibly biological history of the planet simultaneously. Throughout these operations, every measurement, observation, and analysis was guided by a calm and deliberate philosophy. The mission prioritized accuracy, reproducibility, and cautious interpretation over sensationalism. Unlike fictional depictions of instantaneous discovery, the Perseverance mission embodies the patient accumulation of evidence, a steady unfolding of understanding that respects the complexity of the scientific questions at hand. Each data point was a whisper from the past, an invitation to explore, to question, and to imagine the environments in which life might once have existed. In parallel with chemical analysis, environmental monitoring continued. Radiation sensors, temperature probes, and atmospheric instruments recorded current conditions, providing essential context for interpreting the geological record. Understanding the present environment of Mars allowed scientists to assess how well potential biosignatures could be preserved and to anticipate the chemical alterations that might have occurred over time. By integrating environmental data with direct rock analysis, the mission achieved a holistic perspective, linking current Martian conditions to those of billions of years ago. The cumulative effect of these early experiments was profound. Even in the absence of direct evidence of life, the subtle chemical and mineralogical signals began to construct a narrative of habitability. Water-rich environments, protective sedimentary layers, and complex chemical interactions painted a picture of a planet that, in its distant past, may have been capable of sustaining microbial communities. The precise methodical work of Perseverance offered a bridge between the imagination of possibility and the rigor of empirical science. As the rover continued its work, each new measurement raised additional questions. Variations in mineral composition between adjacent rock layers prompted investigations into deposition processes and chemical interactions. Differences in elemental ratios hinted at environmental fluctuations, possibly reflecting changes in water chemistry, climate, or sediment sources over time. Each of these observations added nuance to the understanding of Mars's geological and potentially biological history, highlighting the interplay between chemistry, physics, and the potential for life. In examining the initial findings, scientists began to prioritize locations for more intensive study. Areas with high concentrations of clay minerals, carbonate deposits, or unusual chemical gradients were identified as prime targets for deeper drilling and sample collection. These regions offered the greatest potential for preserving biosignatures, allowing the rover to focus its efforts efficiently while maintaining the broader goal of comprehensive mapping. The strategic selection of study sites exemplified the mission's careful balance between exploration and targeted scientific investigation. Even as initial experiments provided hints of the past, the mission's ultimate goal remained the systematic collection of evidence capable of answering the central question: did life ever exist on Mars? Each rock analyzed, each spectrum collected, and each sample sealed for return contributed to a growing archive of knowledge, forming the foundation for the next stages of investigation. Perseverance, through its instruments and careful methodology, functioned as both observer and investigator, translating the silent history of Martian sediments into data comprehensible to human scientists. Throughout this phase, the focus remained on the convergence of multiple lines of evidence. Chemical analyses were corroborated with microscopic imagery, mineralogical studies cross-referenced with sedimentary context, and environmental data integrated with geological findings. This multifaceted approach reflects the complexity of detecting potential biosignatures, ensuring that interpretations are grounded in a comprehensive understanding of both biological and abiotic processes. The patient accumulation of such evidence exemplifies the documentary spirit of exploration, rigorous, deliberate, and immersive. As these early operations continued, subtle patterns began to emerge. Certain mudstones revealed gradations in chemical composition, while microscopic textures suggested the possibility of past microbial influence. Variations in isotopic ratios provided additional hints of environmental conditions favorable to life. Each of these discoveries, while individually tentative, collectively began to build a narrative of a planet that had once been dynamic, chemically active, and potentially habitable. The rover's instruments, through precise and patient observation, allowed scientists to explore this story in remarkable detail. In the quiet stillness of Jezero Crater, Perseverance worked with methodical diligence. Its experiments were not dramatic in the cinematic sense, yet each measurement, scan, and collection contributed to the unfolding story of Mars's past. The careful observation of sedimentary layers, the mapping of mineral distributions, and the analysis of chemical traces formed a cumulative narrative, a slow, deliberate reconstruction of an environment that had long since ceased to flow, but whose history persisted in stone. By the end of the initial phase of experimentation, the foundation was laid for the next stage of discovery. Samples collected and analyzed on Mars would eventually inform laboratory studies on Earth, where the full range of scientific tools could probe for microfossils, organic compounds, and isotopic evidence with unparalleled precision. The data already collected, however, had begun to illuminate the complexity and potential habitability of ancient Mars, providing glimpses of a world that had once been more than a barren landscape. Perseverance, through its careful, deliberate work, had opened a window into the past, a bridge between possibility and evidence, imagination and science. The mission's approach exemplifies the philosophy of exploration, patience, precision, and cumulative understanding. Each experiment, each scan, and each sample collected represents a deliberate step toward answering one of the most profound questions in planetary science. As the rover continues its work, it carries not only instruments but the weight of human curiosity, translating the silent chemical and geological records of Mars into knowledge that will resonate for generations. As Perseverance methodically cataloged each rock, analyzed each chemical signature, and documented every sediment layer, a subtle narrative began to emerge. A story written not in words, but in the silent geometry of minerals, the faint traces of organic molecules, and the isotopic whispers preserved over eons. The rover's instruments had begun to illuminate the intricate tapestry of Mars's past, revealing environments where life might once have thrived, yet leaving open the profound question of whether any traces had truly endured the passage of billions of years. With each new data point, the possibilities expanded. Was the delicate layering of mudstones merely a record of water's movement? Or did it also encode the fleeting existence of microbial communities? Could the chemical gradients and mineral associations hint at processes driven by life itself? Or were they the elegant outcomes of planetary chemistry acting over immense spans of time? Each answer seemed to raise further questions, deepening the mystery and heightening the sense of exploration. The implications extended beyond the rocks under the rover's wheels. Every analysis hinted at a Mars that had once been dynamic, vibrant, and chemically complex, a planet that bore striking parallels to early Earth. Understanding these chemical footprints might not only reveal the history of Martian life, but also illuminate the broader processes that govern planetary habitability, the emergence of biospheres, and the fragile interplay between environment and biology. Yet, even as Perseverance continued its careful work, scientists recognized that the true depth of the story could not be fully uncovered on Mars alone. Some secrets required the controlled precision of Earth-based laboratories, the ability to scrutinize samples with tools far beyond the capabilities of any rover. The rocks collected in Jezero Crater represented a bridge between worlds, tangible evidence preserved for future study, carrying within them the potential to answer questions that had long captivated human curiosity. This realization set the stage for the next chapter of exploration, a journey not only through Martian sediments, but into the very chemical architecture of life's potential. As scientists prepared to examine these samples in greater detail, the subtle traces identified by Perseverance beckoned, promising insights into processes that occurred billions of years ago, long before Mars became the cold, arid planet we observe today. The path forward demanded patience, precision, and the persistent curiosity that drives scientific discovery. What might these ancient rocks ultimately reveal? Could the chemical and mineral signatures preserved within them constitute the first concrete evidence of life beyond Earth? Or would they instead highlight the remarkable complexity of planetary processes unassisted by biology? The answers lay ahead, waiting to be decoded with the same careful attention and calm determination that had guided every stage of the mission thus far. As we step closer to unlocking these secrets, the stage is set for a deeper exploration of Mars's chemical archives, a journey that promises to intertwine geology, chemistry, and the tantalizing possibility of life in ways that will continue to captivate and intrigue. The silent testimony of Martian rocks invites us onward, urging humanity to listen, observe, and discover in the patient, methodical rhythm that defines true scientific inquiry. The collected Martian rock samples, transported meticulously by Perseverance from Jezero Crater, now represented more than inert fragments of red stone. They were time capsules, potentially holding chemical whispers of a world long past. Upon their arrival at Earth-based laboratories, these ancient sediments began their slow transformation from mystery to data, an unfolding narrative written in atomic patterns, mineral structures, and isotopic ratios. The laboratories represented the ultimate stage in the search for ancient Martian life. Equipped with instruments far beyond the capabilities of any rover, they could probe the samples at the microscopic and atomic levels, searching for the faintest traces of biological activity. Among these tools, isotopic analysis stood as one of the most powerful. Life on Earth processes carbon and other elements in ways that leave subtle but consistent patterns. For instance, living organisms prefer lighter carbon isotopes, creating a small but detectable imbalance when compared to purely geological samples. When samples from Jezero Crater entered these instruments, scientists began the painstaking process of measuring the ratios of carbon-12 to carbon-13. Early results revealed slight but consistent deviations, anomalies that could suggest biological processes at work billions of years ago. These variations alone did not confirm life's ancient presence, but they became a key thread in the larger investigation. The challenge was to ensure that these isotopic patterns were not simply products of unique Martian geology or chemical weathering, but something more profound. Electron microscopy provided another layer of insight, allowing scientists to peer deep into the rock's internal structures. Within the fine-grained layers of mudstone, they found intricate microstructures, tiny filament-like patterns embedded in mineral matrices. These structures bore a striking resemblance to microbial mats found in ancient Earth environments, where layers of microbes formed and fossilized over time in sediment. The repeating patterns of these filaments, their regular spacing, and their preservation in the sediment hinted at processes that were organized rather than random. The presence of matrix-supported mudstones in Jezero Crater further elevated scientific interest. These rocks were formed in ancient calm water environments, perfect for the slow deposition of fine particles. Their laminated structures suggested minimal disturbance over millions of years, an ideal condition for preserving any chemical or biological history they held. Unlike the coarse, chaotic deposits formed by violent processes, these mudstones told a quiet story of time passing, layer upon layer, trapping whatever traces of life may have once been present. Mass spectrometry offered yet another window into the ancient world. By breaking down the rock samples into their elemental and molecular components, scientists searched for trace organic molecules, compounds often associated with biological processes. Small concentrations of carbon-containing compounds were detected, including aromatic hydrocarbons and simple organics. While the presence of such molecules could arise from non-biological processes, their specific arrangement and association with certain mineral patterns raised curiosity. Beyond the detection of molecules, the real challenge lay in interpretation. The science of distinguishing between abiotic and biotic origins of mineral structures was delicate and complex. Abiotic chemical reactions can form surprisingly lifelike patterns. Mineral precipitation from water flowing through porous rock can create filamentous structures that mimic fossilized microbial forms. Isotopic ratios, too, can be influenced by purely geological factors such as temperature, pressure, or volcanic activity. Each data point demanded careful contextual analysis as scientists weighed the likelihood of biological versus geological origins. The debate among scientists was measured and methodical. No single discovery stood out as irrefutable evidence. Instead, the narrative was built cumulatively, with each finding: carbon isotope anomaly, organic molecule detection, microstructure resembling microbial mats, forming a growing tapestry of possibility. As one researcher explained, these results were not definitive proof, but part of an evolving picture, one that required patience and cautious interpretation. With each new piece of data, the broader context of planetary habitability began to take shape. Mars, once home to flowing rivers and standing lakes, had exhibited the key ingredients thought necessary for life: liquid water, chemical energy sources, and essential elements such as carbon, hydrogen, oxygen, phosphorus, and sulfur. The ancient environment of Jezero Crater had been particularly favorable, with its fine sedimentary layers acting as natural preservers of chemistry and history alike. Importantly, the chemical mapping of the samples began to reveal subtle gradients, variations in the concentration of elements like iron, sulfur, and phosphates across different layers. These gradients resembled those formed by microbial communities on Earth, where organisms mediate redox reactions to extract energy, leaving behind patterns of mineral distribution over time. The similarities were striking, but scientists remained cautious, emphasizing that geological processes could also create comparable patterns under certain conditions. Even as data analysis advanced, the philosophical implications of the research came into sharper focus. What exactly constitutes a biosignature? Was it the presence of a single compound, a microscopic structure, or an isotopic imbalance? Or did it require the convergence of multiple lines of evidence, a kind of scientific triangulation that pointed more convincingly toward life? Every subtle anomaly raised these fundamental questions, deepening the sense of mystery and wonder. The broader significance extended beyond Mars itself. If these chemical footprints truly hinted at ancient life, they would not merely rewrite the history of a distant planet. They would expand the very definition of where and how life can exist in the universe. A discovery of life's ancient traces on Mars would suggest that biology is not a rare accident, but a natural consequence of planetary chemistry, emerging whenever conditions permit. As the analyses continued, scientists remained acutely aware of the stakes. Every sample examined was a precious fragment of the cosmos, a whisper from a world that once teemed with possibilities. The patient scrutiny applied to each finding reflected a commitment not to sensationalism, but to scientific rigor. Ultimately, the search for biosignatures became not a quest for a single moment of discovery, but an ongoing journey of revelation. Each experiment added a brushstroke to the canvas, subtly coloring the image of Mars not as a sterile red desert, but as a planet that may have cradled life long ago. The chemical footprints preserved in Jezero crater's ancient sediments thus became silent testimonies, waiting to be read, interpreted, and understood. The story was not complete, but the adventure continued, driven by humanity's enduring curiosity and the steady rhythm of exploration. Beyond the boundaries of the Red Planet, a more profound question began to take shape. If Mars once harbored life, what might this reveal about the universe itself? Could the emergence of life be a rare cosmic accident or a natural consequence of planetary chemistry unfolding across the stars? The possibility that we are not alone stirred a quiet awakening in scientific thought, a universe suddenly alive with potential, waiting for humanity to notice. For centuries, humanity has looked at the night sky, wondering if the Earth's vibrant tapestry of life was unique, or if somewhere else, amid the silent rocks and cold expanses, life might also have taken hold. Until recently, Mars appeared as a quiet witness to the solar system's past, a dry red world, its valleys and plains catalogued as geological oddities, its ancient rivers long dried, a place where life seemed improbable. The subtle patterns discovered in Martian sediments challenge this notion, suggesting that the story of life may have played out beyond our own planet. Imagine a time over 3 billion years ago, when the young sun shone more warmly, and Mars, like Earth, enjoyed temperate climates and flowing water. Shallow lakes mirrored blue skies, winds carried gentle ripples across mudflats, and minerals settled in placid layers that would later preserve the whispers of life. Microbial communities could have thrived in these environments, forming subtle chemical imprints as they consumed, transformed, and reproduced. These traces, once imperceptible, now appear through the careful lens of human exploration, revealed as faint hints in mineral gradients and isotopic ratios. The thought is profound. Life may not be confined to the uniqueness of Earth's conditions. If Mars, in its distant past, could harbor even the simplest forms of life, the universe itself transforms from a vast, empty expanse into a stage upon which biological processes can quietly unfold. Life, it seems, may be less an extraordinary accident and more a natural outcome when the right conditions align. This possibility invites reflection not only on the nature of Mars, but on the very principles by which life arises, on the potential universality of biological emergence wherever water, chemistry, and energy converge. One can picture microbes nestled within warm, mineral-rich pools, metabolizing chemicals and leaving behind the faintest chemical signatures. Each trace, imperceptible to the naked eye, becomes a testament to existence, preserved in fine-grained sediments, waiting billions of years for a chance to be discovered. These are not the grand fossils of dinosaurs or the towering trees of Earth's forests. They are whispers, tiny and humble, yet profound in their implications. In these quiet signals, the universe seems to hint at its own capacity for life, an invitation to those willing to listen. The possibility of Martian life reframes our understanding of biology and evolution. On Earth, life emerged within complex networks of ecosystems shaped by gravity, atmosphere, and climate. On Mars, The parameters were different: weaker gravity, thinner atmosphere, and intense radiation following the loss of its magnetic field. Yet even within such constraints, life could have found a way, protected within sediments, shielded in subsurface pockets, and leaving chemical footprints that endure to this day. In considering these scenarios, humanity is challenged to expand its definition of habitability, of where life might survive, and of the subtle ways it leaves its mark on the geological record. Beyond the scientific implications lies a philosophical resonance. If life once existed on Mars, even at a microbial scale, it implies that biology is not a rare miracle, but a recurring phenomenon, appearing wherever conditions permit. The cosmos, once regarded as a silent vacuum, becomes imbued with stories, some long extinct, some waiting to be found. The search for life thus transforms from a quest for novelty to a profound exploration of possibility, a meditation on existence itself. Every mineral layer, every isotopic ratio, every chemical anomaly becomes part of a larger narrative, connecting humanity's curiosity with the distant past of another world. The challenge, of course, is in interpretation. The faint chemical imprints detected on Mars are subtle and often ambiguous. Minerals can mimic the patterns of biological activity, and organic molecules can arise through purely chemical processes. Yet it is precisely this subtlety that makes the discovery compelling. The scientific method, patient and meticulous, allows humanity to discern what is extraordinary from what is ordinary, to weigh probabilities, and to construct narratives grounded in evidence. Through this careful scrutiny, Mars begins to whisper a story, one not shouted in headlines but quietly persistent, hinting at a universe where life may be more common than previously imagined. As the Perseverance rover's findings continue to unfold, the broader context of planetary science comes into focus. Mars serves as both mirror and contrast to Earth, demonstrating the diverse outcomes of planetary evolution. While Earth's life flourished, diversifying across continents and oceans, Mars may have experienced a fleeting bloom, leaving only the most delicate traces behind. Yet even these traces, captured in chemical and mineral patterns, offer insight into the possibilities of life elsewhere. They suggest that planets, far beyond our solar system, may host their own narratives, written in the language of chemistry and geology, awaiting discovery by future explorers. Ultimately, the universe awakened by possibility is a universe that challenges assumptions. Humanity, having long regarded life as confined to the blue planet, now confronts the tantalizing idea that it might emerge wherever the right conditions exist. The faint chemical footprints on Mars act as both evidence and invitation, encouraging scientists, thinkers, and dreamers alike to consider life as a phenomenon not bound to Earth, but as a potential thread woven throughout the cosmos. It is a subtle, quiet awakening, one that reshapes perspective, inspires inquiry, and elevates the search for understanding into a reflection on our place in the universe. As we contemplate these possibilities, the quiet deserts and sediment layers of Jezero Crater take on a new significance. They are not simply rocks and dust. They are witnesses to a potential history of life beyond Earth, repositories of chemical stories that link the Martian past to the cosmic present. Every analysis, every experiment, every carefully collected sample brings humanity closer to grasping a truth that may extend far beyond the solar system. That life, in some form, may be a common thread, stretching across worlds, waiting to be noticed, understood, and cherished. In the calm reflection of these discoveries, the mind drifts beyond Mars, beyond our solar system, and into the broader universe. Each planet, moon, and asteroid becomes a potential stage for life's emergence, each discovery a reminder that existence may be far richer, more intricate, and more interconnected than previously imagined. The possibility that life is not unique to Earth transforms our relationship with the cosmos, from passive observers to active participants in the unfolding story of existence, called to explore, understand, and reflect on the silent narratives written in stone, ice, and chemical trace across the stars. Yet amid this awakening to cosmic possibility, a subtle tension emerges. Life, wherever it arises, must contend with an unforgiving universe. On Mars, this reality was never more apparent than in the slow disappearance of its once temperate environments. The planet's atmosphere, thin and fragile, offered little protection against the sun's relentless bombardment of high-energy particles. Temperatures swung dramatically, from bitter cold in the long nights to fleeting warmth under the sun, leaving no margin for error for any organism attempting to survive on the surface. Beneath these stark conditions, ancient microbes, if they existed, would have confronted an array of invisible adversaries. Solar radiation penetrated shallow sediments, breaking apart delicate organic molecules and eroding complex chemical structures over millennia. Even modest bursts of charged particles, harmless to hardy rocks, could have been lethal to fragile, single-celled life. The very building blocks of existence, the amino acids, nucleotides, and proteins that form the foundation of biology, were at constant risk, exposed to the slow but persistent forces of decay. Yet Mars may not have been entirely devoid of refuge. Beneath sediment layers and within hidden aquifers, pockets of protection could have allowed microscopic life to endure far longer than surface conditions would suggest. These subterranean havens, insulated from radiation and temperature extremes, might have preserved not only organisms, but also their chemical signatures. In these sheltered spaces, water could linger, minerals could stabilize delicate molecules, and subtle chemical gradients could persist, a quiet testament to the resilience of life under the harshest conditions. The fragility of life on Mars also invites reflection beyond its borders. In contemplating other worlds, icy moons orbiting distant gas giants, rocky exoplanets bathed in the light of young stars, we realize that life's tenuous grip is likely a universal struggle. The same forces that shaped the fate of Martian microbes, the interplay of radiation, chemical availability, temperature, and geological stability, play out across countless worlds, many of which we have yet to observe. Mars thus becomes both a case study and a cautionary tale, illustrating the delicate balance required for life to take hold and persist. Despite the planet's challenges, the faint traces recorded in Jezero crater offer hope. Every layer of sediment, every carefully preserved chemical signature, is a testament to what might have existed and to the subtle ways life leaves its mark even under extreme stress. Patterns in minerals, distributions of organics, and isotopic anomalies hint at processes that may have been biologically mediated. While these hints are not conclusive proof, they represent the remarkable capacity of life, even in its simplest forms, to adapt, persist, and record its existence for future observers. The story of Mars's ancient life is therefore one of both fragility and endurance. It is a narrative written in stone, in the delicate chemistry of sediments, and in the whispers of molecules that have survived billions of years. It demonstrates that life, though vulnerable, is not easily erased. Its traces, however subtle, provide a bridge across time, linking the silent Martian past to the curiosity of the present. Ultimately, the fragility of life on Mars underscores the immense challenges faced by organisms across the cosmos. Even planets that once harbored conditions favorable to biology are subject to slow, inexorable forces that can erase the most delicate forms of existence. Yet in recognizing this fragility, there is also a deeper appreciation for the resilience of life, the ability of even the smallest organisms to endure, leave traces, and hint at worlds that were once vibrant with activity. Mars's story becomes a lens through which we can examine our own place in the universe. If life emerged there, it may also emerge elsewhere, adapting to conditions we might not yet fully understand. Every hint preserved in Jezero crater's sediments becomes a reminder that existence is not guaranteed, yet when it does occur, it can leave echoes that resonate across space and time, waiting for humanity to uncover them. The quiet resilience of potential Martian life encourages reflection on the delicate balance of ecosystems across all planets, including our own. It is a reminder that life's survival is neither trivial nor assured, and that the fragility witnessed on Mars may well mirror the precariousness of life throughout the cosmos. Each discovery on the red planet, each chemical signature interpreted from ancient rocks, deepens our understanding not only of Mars, but of the universal conditions that allow life to flourish, persist, and sometimes fade into silence. In this contemplation of vulnerability and endurance, the broader significance emerges. Life is simultaneously delicate and astonishingly persistent. Mars's ancient story invites us to marvel at the interplay of chemistry, geology, and biology, and to appreciate the extraordinary circumstances under which life might arise elsewhere. The insights gained here extend beyond our solar system, hinting at a universe where the delicate balance of survival shapes every world touched by starlight. If even the faintest traces of life could survive, or leave a record, on a planet as unforgiving as Mars, then perhaps life elsewhere is not so improbable. What might this suggest about the abundance of life across the cosmos? Could distant moons, exoplanets, or hidden oceans also harbor silent witnesses to biological processes? These questions beckon humanity to look outward with curiosity, humility, and wonder, preparing us to consider the profound possibility that we are not alone. Consider the implications. If microbial life arose independently on Mars, even in its brief window of habitability, it suggests that the emergence of life may not require extraordinarily rare circumstances. Life, in this view, could be a natural consequence of the right combination of elements, energy, and time. Mars, with its water-rich past and chemically diverse sediments, becomes a proof of concept, a neighboring planet that hints at the universality of life's potential. For decades, the rare Earth hypothesis has guided scientific thought, emphasizing Earth's seemingly unique combination of stabilizing factors: plate tectonics that recycle nutrients, a protective magnetic field that shields from cosmic radiation, oceans that buffer climate, and a star with steady output. According to this perspective, complex life is rare, perhaps nearly impossible elsewhere, but the subtle chemical and mineral clues left in Jezero crater challenge this assumption. If life could emerge, even briefly, on a world as harsh as Mars, the cosmos might be far more fertile than previously imagined. The philosophical implications are profound. Humanity has long regarded itself as alone, perched on a singular cradle of life. The notion that biology could arise elsewhere forces a reevaluation of our cosmic significance. Earth may be precious, but not unique. Life could be quietly flourishing, or have flourished, on countless worlds we have yet to explore. Each planet, moon, and exoplanet becomes a canvas shaped by chemistry and energy, where life might write its own story. Consider the icy moons of the outer solar system. Europa, with its subsurface ocean hidden beneath a frozen crust, presents a tantalizing prospect. Tidal forces from Jupiter create energy fluxes that could sustain microbial ecosystems in liquid water pockets far below the ice. Enceladus, with its plumes of water vapor venting into space, offers a direct glimpse into potential habitats and chemical signatures that hint at subsurface life. Titan, with methane lakes and complex organic chemistry, may host entirely different biochemistries, offering a mirror into possibilities beyond Earth-centric life. If life is possible there, the universe becomes a network of hidden biospheres, each shaped by its environment but united by the fundamental chemistry of life. The presence of life beyond Earth is not merely a scientific question, it is an ethical one. Discovering extraterrestrial microbes, even in trace amounts, compels humanity to consider our role as explorers and stewards. How should we approach these fragile ecosystems? Every probe, every drill, and every experiment carries the risk of contamination. The search for knowledge must be balanced with responsibility, acknowledging that life, if it exists elsewhere, is both precious and vulnerable. Reflecting on Mars itself, the potential traces of ancient microbes serve as a reminder of both resilience and impermanence. Life may emerge quickly when conditions permit, yet it can be equally fragile in the face of environmental change. Mars, once capable of supporting microbial ecosystems, eventually became inhospitable. The lessons extend beyond our neighboring planet. Life is a fleeting yet persistent force, dependent on a delicate balance of planetary conditions. As we extend our gaze to distant exoplanets, the possibilities multiply. Thousands of planets have already been identified orbiting other stars, some within the so-called habitable zone, where temperatures allow liquid water to exist. Could these worlds host microbial colonies, oceanic ecosystems, or entirely novel forms of life? The faint chemical imprints on Mars inspire us to seek these distant whispers of biology, to read the subtle signatures encoded in atmospheres, reflected in light spectra, or hidden in ice and rock. Yet even as we dream of discovery, we are reminded that life is not guaranteed. The same processes that create opportunity, volcanism, flowing water, chemical gradients, can also destroy. Radiation, planetary cooling, atmospheric loss, and catastrophic impacts all challenge survival. Life's persistence is a delicate negotiation between possibility and peril, a narrative of endurance that might echo across the cosmos or remain an isolated experiment in biology. In this light, the potential of life on Mars becomes both inspiring and humbling. It invites us to explore not with arrogance, but with patience and reverence. Each sample analyzed, each chemical anomaly investigated, is a chapter in a story that may span the galaxy. By studying Mars, we learn not only about a neighboring planet, but about the conditions that make life possible and the resilience required to endure over geological time. The question, "Are we alone?" is no longer confined to abstract philosophy. It is anchored in evidence, in chemical footprints, in sedimentary archives, and in patterns that hint at processes once driven by living organisms. Mars offers the first tangible clues in this vast inquiry, a laboratory for understanding the likelihood and limits of life beyond Earth. Ultimately, the possibility of life elsewhere transforms our perspective. The universe, once considered silent and inert, appears as a place of potential, an intricate web of chemical processes and environmental niches where biology may flicker into existence. Humanity's task is to observe, interpret, and learn, guided by the delicate traces left by life itself. Each discovery on Mars, each lesson from a distant moon or exoplanet, adds to a growing narrative that life may be a common, persistent feature of the cosmos, quietly shaping worlds, leaving subtle signatures, and awaiting discovery by those patient enough to seek it. Mars becomes the doorway to a broader understanding that life, though fragile, may be widespread, that the universe is not silent but alive with possibility, and that our exploration is a journey into the very essence of existence itself. The red planet whispers a quiet message. Life is tenacious, yet delicate, fleeting, yet persistent. A story written in stone, ice, and chemical trace, waiting for humanity to read it. Even as the mind marvels at the potential of life across the cosmos, a quieter voice emerges, one of restraint and careful reflection. The excitement inspired by possible biosignatures on Mars is tempered by the lessons of history. Earlier claims, from the Viking lander experiments to the controversial ALH 84001 meteorite, remind us that the path to discovery is rarely straightforward. Science advances not through speculation alone, but through meticulous verification, critical analysis, and measured interpretation. Every anomaly, every unusual chemical pattern must be placed in context. Was it shaped by life, or by the patient forces of geology and chemistry over billions of years? The distinction is subtle, often microscopic, demanding a discipline that balances curiosity with caution. It is a reminder that even as the universe offers tantalizing hints, truth must be separated from possibility with rigor, and wonder must coexist with skepticism. As humanity continues to explore Mars, collecting samples, mapping sediments, and interpreting chemical footprints, the broader journey is as much philosophical as it is scientific. We are called not only to imagine life beyond Earth, but to approach each claim, each clue, with the diligence and humility that ensure our understanding remains grounded. The whispers of ancient Martian life are compelling, yet they demand patience, discipline, and the steadfast practice of science, a careful watchfulness that weighs every observation against centuries of accumulated knowledge. In this way, the story of Mars becomes a meditation on both possibility and responsibility, the promise of discovery intertwined with the imperative of caution, guiding humanity toward truths that are as profound as they are elusive. Even as the promise of life on Mars inspires wonder, the practice of science demands a steady hand, a measured approach, and a recognition of the lessons embedded in history. Human curiosity is vast, but it must be tempered with the discipline of verification. The history of Martian exploration provides a careful reminder: extraordinary claims require extraordinary evidence. The Viking lander, touching down in the 1970s, carried instruments designed to detect life, yet the results remained ambiguous, fueling decades of debate. Later, in the 1990s, the ALH 84001 meteorite appeared to offer a tantalizing clue: tiny structures and chemical patterns that some interpreted as fossilized microbes. But the controversy it ignited highlighted the ease with which hope can outpace evidence. From these episodes, the scientific community drew a critical lesson: patience is essential. No single data point, no matter how intriguing, is enough to redefine our understanding of life. Claims must be examined across multiple lines of evidence, tested, retested, and corroborated by independent researchers. Each discovery becomes a thread woven into a broader tapestry of knowledge, and only when patterns converge, when repeated observations point to a consistent story, can confidence begin to grow. The challenge is not only procedural, but also conceptual. On Mars, the distinction between a chemical pattern arising from life and one formed through geological or chemical processes is remarkably subtle. Filament-like mineral structures, complex organic molecules, and isotopic anomalies may mimic the signatures of microbial activity, yet could also emerge from non-biological mechanisms over billions of years. Untangling these possibilities requires an extraordinary combination of skill, technology, and imagination, a willingness to follow the evidence wherever it leads, even when it contradicts initial expectations or cherished hypotheses. Advanced laboratory techniques performed on Earth now complement the analyses conducted by rovers like Perseverance. Mass spectrometry, electron microscopy, and isotopic ratio studies allow scientists to probe Martian samples at scales and resolutions impossible on the planet itself. These methods reveal chemical gradients, mineral associations, and molecular arrangements that hint at processes that occurred long before humans ever gazed skyward. Yet, even these powerful tools demand careful interpretation. Science, at its heart, is a practice of questioning, of scrutinizing, of distinguishing signal from noise. In this context, the search for life is as much a philosophical endeavor as a technical one. It requires humility, a recognition that nature can surprise, confound, and challenge even the most careful observer. The act of claiming life demands certainty that is almost unattainable, a threshold deliberately set high to prevent error, misinterpretation, or premature celebration. In Mars's silent deserts and ancient lakebeds, patterns emerge that provoke curiosity, but none can be considered proof in isolation. Each must be weighed against geological plausibility, chemical processes, and environmental context. Historical episodes offer instructive caution. The Viking lander's experiments, designed to detect metabolism, produced signals that could be interpreted in multiple ways. Some suggested microbial activity, while others pointed to reactions in the soil unrelated to life. The ensuing debate illustrated the difficulty of assigning biological meaning to complex chemical results, especially in alien environments. Similarly, the ALH 84001 meteorite, with its tiny carbonate globules and purported microfossils, captivated both scientists and the public. Yet decades of analysis revealed that non-biological processes could plausibly account for many of its features, reinforcing the lesson that extraordinary claims must withstand extraordinary scrutiny. These examples underscore a fundamental principle. Science progresses incrementally, not instantaneously. Discoveries are not isolated moments of revelation, but cumulative, evolving understandings built from careful observation, replication, and debate. On Mars, this approach ensures that every mineral map, every isotopic measurement, and every microscopic image is considered in context, evaluated with skepticism, and integrated into a larger narrative that respects both the data and the unknown. The delicate balance between curiosity and caution shapes every step of exploration. While the possibility of life invites imagination, it is scientific rigor that ensures that wonder is not mistaken for certainty. Claims of biological activity must be supported by multiple independent observations, chemical patterns consistent across locations, mineral structures showing organized complexity, and isotopic ratios that defy purely geological explanations. Only when these lines of evidence converge does a hypothesis gain weight. Moreover, the discipline of caution extends beyond Mars. As humanity peers toward icy moons, distant exoplanets, and other corners of the cosmos, the lessons learned from past missions serve as guiding principles. Europa's subsurface ocean, Enceladus's geysers, and Titan's methane lakes all tantalize with the potential for life. Yet the interpretation of any detected signatures will be subject to the same rigorous scrutiny applied to Martian samples. Understanding life elsewhere demands patience, skepticism, and a willingness to embrace uncertainty, recognizing that the universe is complex, subtle, and often deceptive in its signals. Even as technology improves, the conceptual challenge remains. Biosignatures, chemical, isotopic, or structural indicators of life, are not self-evident. They are inferred from patterns, from correlations, from deviations that cannot be easily explained by known abiotic processes. Interpreting these patterns requires not only data, but insight, combining expertise in geology, chemistry, biology, and planetary science. It is an exercise in discernment, a careful weighing of probabilities, where the stakes are nothing less than rewriting humanity's understanding of life itself. This practice of scientific caution is not a restraint on imagination, but a framework that allows discovery to be credible, meaningful, and enduring. It acknowledges the excitement that accompanies new observations while grounding interpretations in reproducibility, peer review, and methodological rigor. It ensures that, when a claim is eventually made, it carries the authority of evidence, not the weight of speculation. In the vast silence of Martian plains, where dust drifts slowly across ancient rocks and layers of sediment hold chemical whispers from billions of years ago, the search for life unfolds as a careful dance between curiosity and discipline. Each anomaly is examined, each pattern questioned, and each potential biosignature evaluated within a broader geological and chemical framework. This deliberate approach may seem slow, almost painstaking, but it is precisely this patient scrutiny that transforms intriguing hints into robust understanding. Ultimately, the weight of scientific caution preserves the integrity of exploration. It prevents the premature celebration of findings, safeguards against misinterpretation, and maintains a clear path toward genuine discovery. By adhering to these principles, scientists ensure that, when the first definitive signs of life beyond Earth are identified, humanity can recognize and trust them for what they truly are. The story of Mars serves as both inspiration and instruction. A planet that may hold echoes of life, offering profound possibilities, yet demanding the highest standards of inquiry. It is a reminder that discovery is not measured solely in excitement or headline-grabbing claims, but in patience, rigor, and the unwavering commitment to truth. In embracing the weight of scientific caution, humanity strengthens its capacity to listen to the silent narratives of the universe, subtle, fragile, and waiting for those careful enough to understand. Even as this careful attention continues, the horizon of exploration expands. Each sediment layer, each faint chemical trace preserved over billions of years, suggests stories that extend beyond the reach of rovers alone. The next chapter of discovery lies in bringing these Martian samples to Earth, where laboratories can probe with precision instruments, analyze isotopic ratios, and search for organic compounds in ways that were impossible on the planet itself. The future of the search is a balance between curiosity and restraint, imagination and discipline. While technology will open unprecedented windows into Mars' ancient environment, the human element, patient observation, rigorous interpretation, and humility in the face of the unknown remains central. Each step forward is guided by the lessons of the past, the careful study of chemical footprints, and the profound possibility that life may once have flourished on this distant world. In the vast silence of Martian plains, where dust drifts slowly across ancient rocks and layers of sediment hold chemical whispers from billions of years ago, the search for life unfolds as a careful dance between curiosity and discipline. Each anomaly is examined, each pattern questioned, and each potential biosignature evaluated within a broader geological and chemical framework. This deliberate approach may seem slow, almost painstaking, but it is precisely this patient scrutiny that transforms intriguing hints into robust understanding. Every rock collected, every sediment layer analyzed carries a story. The fine grains of mudstone preserved in the calm waters of Jezero Crater eons ago are not merely fragments of a distant world. They are pages in a cosmic diary. Within them lie subtle chemical gradients, minute organic traces, and microscopic textures that hint at processes far more intricate than a simple planetary narrative. The challenge is to read these pages accurately, without imposing human expectation or allowing excitement to overshadow rigor. The upcoming sample return missions promise to bridge the final gap between curiosity and clarity. Rovers, despite their advanced instruments, are ultimately limited by size, energy, and the harsh environment of Mars. On Earth, scientists will have access to high-precision mass spectrometers, synchrotron radiation facilities, cryogenic electron microscopes, and an array of chemical and isotopic techniques that can probe these ancient sediments with unrivaled detail. For the first time, the possibility of testing for subtle isotopic fractionation, complex organic polymer chains, and microfossil-like structures in a controlled environment becomes a reality. Yet even with these advanced tools, the act of interpretation remains deeply human. Each result must be scrutinized within the context of planetary processes, ancient climates, and the chemical tendencies of Martian minerals. A carbon signature alone cannot confirm life. It must be correlated with other lines of evidence, mineral matrices, isotopic ratios, spatial distributions, and chemical associations. It is in the convergence of these multiple data streams that a convincing picture may emerge. This patient and methodical approach is necessary because the stakes extend beyond science. A confirmed biosignature on Mars would reshape human understanding of our place in the cosmos. It would challenge assumptions about the rarity of life, the uniqueness of Earth, and the likelihood of biology emerging elsewhere in the universe. The philosophical weight of such a discovery is immense, prompting reflection on both the possibilities and responsibilities of exploring other worlds. But the search is not merely philosophical. Each step forward teaches tangible lessons about the resilience of life, the interplay between chemistry and environment, and the conditions that allow biological systems to flourish or fail. Mars is a case study, a laboratory in which the variables of planetary habitability are writ large across ancient landscapes. The lessons learned here inform not only the search for extraterrestrial life, but also the understanding of Earth's own biosphere, the fragility of ecosystems, and the subtle conditions that sustain complexity. The careful pacing of this research is a testament to scientific humility. Past claims of life beyond Earth, from the Viking experiments to the ALH 84001 meteorite, remind us that discovery without rigor can mislead and misinform. The Perseverance mission, the collection of samples, and the impending Earth-based analysis reflect a commitment to method over haste, to truth over excitement. Each phase is designed not to produce headlines, but to produce understanding, and in this deliberate progression lies the essence of modern exploration. Beyond the technical and philosophical dimensions, the search also evokes a profound sense of wonder. As humans, we are drawn to the unknown, to stories written in stone and sediment, to chemical patterns that whisper across eons. Each sample, each spectral reading, each isotopic measurement is a dialogue with a world that existed long before our species emerged. It is a reminder that the universe holds narratives far older and richer than our own, and that patient observation allows us to read them slowly and carefully. Consider the possibilities that these samples might reveal. A carbon isotope ratio consistent with biological metabolism could hint at ancient microbes. The discovery of complex organic compounds in association with layered mudstones could suggest chemical environments conducive to life. Microscopic filamentous structures might offer subtle echoes of ancient cellular forms. Even partial evidence, carefully contextualized, has the potential to reshape scientific understanding. And yet, scientists proceed cautiously, aware that each anomaly might have an alternative explanation rooted in geology or chemistry, rather than biology. At the same time, the human dimension of the search cannot be overstated. The endeavor connects generations of explorers, scientists, engineers, and dreamers in a chain of curiosity and discovery. Every technological advance, every meticulous experiment is built on decades of inquiry and imagination. Perseverance itself is the culmination of countless hours of design, testing, and planning, an emblem of humanity's capacity to reach across space and time in search of answers. The samples it gathers will carry forward that legacy, bridging Mars and Earth, past and present, science and imagination. Moreover, these missions are shaping a broader understanding of planetary science. Even if life is not ultimately confirmed, the knowledge gained about ancient Mars, its hydrology, mineralogy, climate evolution, and chemical history, is transformative. Each sediment layer tells a story of environmental change, from flowing rivers to evaporating lakes, from thick atmospheres to thin, desiccated air. The planet itself becomes a narrator, revealing conditions that may inform the search for life elsewhere, on icy moons, exoplanets, or hidden subsurface oceans across the galaxy. The search also challenges humanity to confront uncertainty. Even with advanced instruments and decades of research, definitive answers may remain elusive for generations. Some biosignatures might be ambiguous, some patterns subtle, and some data open to multiple interpretations. Accepting this uncertainty is part of the process. It underscores the importance of skepticism, collaboration, and iterative investigation, hallmarks of science at its most disciplined. Yet the potential rewards justify the painstaking effort. A confirmed trace of life on Mars would extend the reach of biology beyond Earth, fundamentally altering our understanding of evolution, ecology, and the conditions necessary for life. It would provide a second reference point in the universe, a proof that life can emerge elsewhere, and perhaps a guide for where to look next. Even the faintest evidence, carefully validated, can transform human perspective and inspire generations to come. Ultimately, the future of the search is a blend of technology, patience, and imagination. It is a journey that requires meticulous experimentation, rigorous analysis, and philosophical reflection. It is a path that navigates between excitement and restraint, curiosity and caution, allowing humanity to explore boldly while remaining anchored in the principles that have guided scientific discovery for centuries. In the end, the story of Mars, its rocks, sediments, and chemical footprints, serves as both challenge and inspiration. The samples returned to Earth will speak across time and space, inviting scientists to listen closely, interpret cautiously, and dream openly. Each molecule analyzed, each isotope measured, each microscopic structure examined contributes to a growing understanding of life's potential in the universe, the conditions that foster it, and the delicate interplay between biology and environment. The search for life on Mars, while rooted in methodical science, is also a profoundly human endeavor. It reflects our desire to know, our capacity to imagine, and our willingness to engage with the unknown. As new technologies unfold and samples are meticulously examined, humanity stands at the threshold of revelation, poised to learn whether we are alone or whether the universe is quietly teeming with possibilities, waiting for patient eyes to see and careful minds to understand. As we conclude this journey across Mars, tracing the faint chemical whispers of a planet that may have once hosted life, the story of exploration continues. Beyond the rocks, beyond the rovers, beyond our imagination. If this journey through time, science, and discovery has captured your curiosity, consider subscribing to our channel. By subscribing, you ensure that you will not miss future explorations into the mysteries of our universe, from distant planets to the hidden stories written in the stars. Join us as we continue to uncover, reflect, and dream, always guided by curiosity, patience, and the quiet thrill of discovery. Stay with us and let the universe unfold, one story at a time.